So today we are going to look at the TNB frame. And the best way to describe this is picture an airplane flying aerial stunts above you. So if you are on the ground, so you're on that IJ plane, what you see above you is the K plane, and you see the pilot flying in that K plane. And you may see some pretty cool things. You may see him move along the IJK plane. But if you picture your friend who's also watching this pilot but is a mile away, what they see, although they are in the IJ plane, is a different perspective than yours. So how do we describe that motion of that plane more succinctly? Because if we're in that IJ plane, they're both going to be a little bit different. Well, we do that with the pilot's frame of reference. And the pilot's frame of reference is what we call the TNB frame. So let's talk about what T, N, and B represent. Okay, so the T of this is actually something we have talked about before. This is our unit tangent. In referencing that idea of the pilot's point of view, the unit tangent is the direction, I'm not sure why it keeps doing that word glitch, the direction the pilot's heading, or the direction that particle is heading if we're talking about motion in space. Then, if we want to think of this in terms of the plane, picture this as the nose of the plane. Okay, and if we keep going with this analogy, N stands for the unit normal. Remember, a normal is something that's perpendicular to. So the normal is perpendicular to the tangent, or the unit tangent. And this is representative of the direction the plane would be turning. Oh, we don't need to write plane. The direction turning, maybe a particle. And when we think about this in terms of the analogy of the plane, this would be like the tail fin. And you can picture the nose of the plane and the tail fin of the plane are perpendicular to one another. And then finally, we have the unit binormal. Well, if we look at that word binormal, we see that that prefix bi means two. So it's perpendicular or normal to two different vectors. So it's perpendicular to both the T and the N vector. And this is, for lack of a better term, the direction the particle would be twisting. And when we think about this, if we're going to be perpendicular to the nose and the tail fin at the same time, the only thing that could be in our representation of a plane would be the wings. Okay, so this is the TNB frame. So let's look now at how we write equations relating these. Okay, we've looked at T before. T, remember, is that unit tangent vector. And a unit tangent vector means that we're going to be perpendicular to that vector. So we'll say r prime of t. And if I want it to be a unit vector, remember, we need to do the magnitude of r prime of t. So we've looked at that before when we were dealing with the curvature. So let's talk a unit normal vector. Well, a unit normal vector means it's perpendicular to the unit tangent vector. So if I'm going to be perpendicular to the unit tangent vector, means that if I take the derivative of the tangent vector and divide it by the magnitude of the derivative of the tangent vector, I will have my unit normal vector. Now remember, we said B is the binormal, or the unit binormal. If I need to be perpendicular to both, think back to what we need our vectors, or what operation we can do with our vectors to find something perpendicular to both. If you said cross products, you would be right. So if I take the cross product of vector t with the vector n, that will give me my binormal vector. Okay, so let's quickly prove that t and n are in fact perpendicular, that these two vectors are in fact perpendicular. Let's assume that we have some vector that has a constant length. Okay. And if we take and dot product two of the same vectors together, we know dot product is equal to the components multiplied and added together. Do you agree that this would be equal to the magnitude of the vector squared? Remember, magnitude is the square root of each of the components squared. And if we're dealing with the same vector, that makes sense that this would be the magnitude of v squared. So what that implies is that v dot v is also a constant. We good with that? Okay, so now let's take the derivative with respect to t of v dot v and the derivative with respect to t of the constant. Okay, if we do that, there is a rule that says if we're going to take the derivative of two vectors that are dot product, we are going to get the derivative of vector dot product with the vector plus basically the product rule, vector dot product with the derivative of that vector. And then we know the derivative of a constant is 0. So we would get 2 v dot v prime is equal to 0, which means v dot v prime is equal to 0. And because of this, we can say that a vector must be perpendicular to its derivative if it's a constant vector. Okay, so let's go with the idea. The magnitude of t is 1 because we said it is a unit tangent vector. So therefore, following what we just did, then the t dot t prime is equal to 0, since we just proved that, which means that t has to be perpendicular to t prime. So therefore, t has to be perpendicular to n, because t prime over the magnitude of t prime, which just yields it as 1, is perpendicular to n.